All right, welcome back, everyone. It is my pleasure to introduce the next segment, which is a talk that I look forward to every year. And I don't know how this man actually gets the time to do the hacks that he talks about, but they blow me away every year. And if anyone's done it, he definitely has proved that you can make the day have 27 hours if you really work on it. You know him from a website called Sprites Mods, where he does amazing things like hacking the firmware on hard drives and making ancient displays come back to life even though they seem broken through all kinds of bending over backwards. 2 years ago, he showed us how he reverse engineered the firmware on a gaming keyboard and made it do his bidding. Things like giving a pool ripple effect when he had a keystroke and playing Snake on the game. And last year at the SuperCon, he really threw down the gauntlet with the Tamagotchi singularity. I won't describe that for you here because it would be a disservice, but if you don't know what I'm talking about, that should be the #1 thing on your list after the SuperCon. He is currently the senior software engineer at a company called Espressif, which you might know for the ESP8266 and more recently the ESP32. These are small computers that are kind of revolutionizing our ability to build inexpensive and robust wireless devices. Please welcome to the stage Jeroen Domburg, also known as Sprite TM.
Thank you. Thank you. So first of all, my talk on the schedule is Game Boy problems. I don't necessarily have a problem with the Game Boy. The correct title is miniaturizing the Game Boy Color because that's what I did. So first of all, let me, Mike already did a hell of a job in introducing me, so I can mostly skip through these slides. My name indeed is Jeroen Domburg. I am also clicking, the keyboard is just too low. I'm also known as Sprite TM. I run the website Sprites Mods, and at the moment I work for a company called Espressif, which indeed is a purveyor of fine Internet of Things Wi-Fi chips. I also got to do a disclaimer here because the thing I'm going to describe has one of Espressif's chips in it. I have not been paid by Espressif to build this, to do this talk or whatever. They pay me my salary because I work for them. But on the other hand, the ESP32 is somewhat of my baby as well. I did some things that led to modifications in the architecture. I partially developed the SDK that's on it. I did a fair amount of things on it. So I basically, kind of suffer from the IKEA thing. I think the ESP32 is the best thing since sliced bread. Obviously, I'm biased. So here's a disclaimer. If you want to have a chip that can do Wi-Fi, by all means look at Espressif's fine products, but don't take my word for it, obviously. I assume you're all smart people. I assume you can all do your own research, and I hope you do. Okay, so what did I make here? Well, basically, I'm a kid of the 90s, and as most people who grew up in the 90s have, at a certain point, my parents gave me a Game Boy to shut me up on vacations, etc. Initially, that worked like in precisely as planned, as in I played a hell of a lot of games on it, and then I ran into this obscure thing called the internet, and I actually figured out that this is a piece of hardware that actually you can figure out how it works. And initially, I basically figured out I could take a cartridge, I could remove the ROM, I could replace it with a hell of a lot of wires. Unfortunately, I don't have a picture because that thing is back in the Netherlands. Then I could attach a big socket to it, put an EEPROM in there, and I could pirate games. Yeah. So obviously pirating games wasn't all I did. I was interested in the Game Boy. The Game Boy has a Z80 CPU. That thing is pretty programmable. So it wasn't very long until I made my own programs and games. And actually this is one of the games I made. It's still floating around somewhere on the internet. And actually, this game I sent this thing in. There was a company who made Game Boy flashcards, and they had a competition for who could make the most interesting homebrew game. I didn't win, but they gave away a whole bunch of prizes, and one of them was this thing, which is an 8 megabyte flashcard. And I, of course, used this, being the, 14-year-old I was, to pirate even bigger and better games. Nowadays I pay for my games, by the way. So one of the things that also happened in the 80s was the Game Boy was a huge craze, and there were also other products coming out that, capitalized on that. And one of them was this thing. This is a little keychain thing. It's called the Time Boy. And I saw this thing and I thought, this is awesome. I mean, I can have like a little Game Boy on my keychain, and if I'm bored, I can just take my keys and play a little game on it. Well, unfortunately, I pretty quickly found out that the only thing you can do with it is look at it to see the time. So I was so disappointed. I mean, why can't they just take a Game Boy, shrink it a bit, and then make it into something that you can tie to your keychain? Why can't they do that? Well, that was a hell of a lot of time ago. The Game Boy is, the original Game Boy is like 25 years old now. I've grown up, technology has grown, everything has become more integrated, etc. But I still remember that frustration I had with not being able to, tie a Game Boy to my keychain. So I decided to try and see if I can change this. So, basically I wanted to have a miniature Game Boy. So first of all, we should start with the screen, because that's the most important bit of the Game Boy. It's the thing you keep looking at. This is the original Game Boy screen. The original Game Boy screen isn't that impressive. It has 160 times 144 pixels. It has 4 grayscales, which are all equally shitty. And but if anything, I wanted to have something that at least equaled that. So, obviously the display should be pretty small because it needs to fit in something you can hook up to your keychain. It has to have 4 grays or more, because otherwise you can't display the Game Boy stuff. And if anything possible, it should approach the resolution of a real Game Boy. So. I looked around and I went on Taobao, which is the Chinese equivalent of eBay, basically. And I found this really nice OLED screen. It's 800 times 600. The display itself is tiny. It runs from 3.6 volt. Absolutely awesome. Let's buy one. Maybe I should take another look. So I found another display which was way more affordable. This one is pretty nice. It's smaller than 1 inch in diagonal. It's RGB, which is pretty nice. The only unfortunate part is that it's only 96 times 64 pixels. So that may be a problem. Well, there's only one way to find out if it really is, if I can make a Game Boy screen look good on this, and that's to try it out. So this is the initial rig I used. It is, the screen I talked about, connected to an FT232 board, so to say. The FT232 has a mode in which you can bit bang the lines as being GPIO. And I use this to basically simulate an SPI bus to push data to the screen. It's not the fastest way possible, and you get a frame rate of about 1 picture a second, but it works. And I modified an existing Game Boy emulator to push its image to the little display. And by the way, about the FT232, there actually has been a thing about that. You had FTDI Gate, where FTDI decided to brick all fake FT232s. You probably remember that. And I remember from the Hackaday comments that there was a huge issue with people being like, yeah, but I have no idea how I can, know if the FTDI I bought is a fake or a real one. Well, actually, I have no such problems. I have the ideal solution. What I do is I go on Taobao, I look for these tiny boards, and damn it, sorry. And they're like $2 a piece, and for this price, I'm absolutely 100% sure these are fake. I have no problem distinguishing them. So, onto the results, and it actually looks like this, and this is by all means acceptable. As I said, the frame rate is about 1 frame a second, so it's not really playable, but you can see what you're doing. So I decided that this would be good enough to make a miniature Game Boy. So I bought a whole bag of those displays. I mean, you saw the price, it's not that expensive. And what I did is, this screen is basically gonna be a measurement for the dimensions of the Game Boy. So what I did was I took the dimensions of the screen, the dimensions of the visible area, put that all into Inkscape, took an image from an existing Game Boy Color, and basically scaled that image until it fit the screen. So from there I could get measurements for the buttons and all the other things. So I bought a whole bunch of buttons. I bought a speaker. I was actually really surprised that you can get a speaker with a diameter of less than 1 centimeter, but there you go. I bought a battery. Initially, Taobao sent me to this. That probably is not a good idea, especially not because I would have an issue with bringing the Game Boy here, because when I stepped on the plane in Shanghai, I literally, this is the thing we ran into on the check-in thing. Make sure you don't take any drugs or Galaxy Note 7s on the plane. So, I decided to go with a slightly less well-known battery. This one is pretty small, but it still contains like 150 milliamp hours, which I think currently it should allow the Game Boy to run for an hour or so. So that's enough for a keychain, I would say. And finally, I got one of the ESP Room 32 modules from work. And this is basically a module we make which integrates the ESP32 chip, which is the new chip we make. Just the specifications, it has two CPU cores, both can run on 240 megahertz. It has about 0.5 megabyte of RAM. You can use all of that as data RAM, but a fair amount of it you can. It has a whole slew of peripherals, timers, UARTs, etc. And, the most important bit, it can do Wi-Fi and Bluetooth, which I don't really use for this project, but there you go. So I got all the components, and then I had to decide. Then I had to design a PCB. So obviously I knew the size and the position of all the components, like in the buttons, etc. So we could design a PCB. This is it. It was kind of sort of irritating because I actually had to lead the flex cable for the display through the PCB. There's a hole in the middle there. But the problem is that all the connections to the ESP32 has to go around that. So that was pretty frustrating to do. But in the end, I figured out a way where it would work. So what's on the PCB? Well, this is part of the schematic. This is the power supply. It basically has 3 parts. The top part is a box standard lithium-ion charger. I use a TP4057, which is, I think it's a Chinese knockoff of some analog devices chip or something. It basically is a lithium-ion charger. You put 5 volt into it and it'll charge a lithium-ion battery. The middle part is a 3 volt LDO, which generates the power that supplies all the digital parts. And the bottom thing is a boost converter, because the OLED display also needs 14 volts to actually drive the LEDs that are on there. Also, both the boost converter as well as by the way, there's a MOSFET in there to make sure that if you shut the entire thing down, the 14 volt actually drops to 0. Both the boost converter as well as the LDO have an enable input, and I actually use that. The microcontroller can control this line to basically cut its own power supply. So this is the main logic part. You have the OLED display, which of course gets fed by 3.3 volt and 14 volt, and has an SPI interface to the ESP-ROM32. The ESP-ROM32 also is connected to the buttons. A few of them have external pull-ups because the thing doesn't have internal pull-ups on all pins. And finally, this is the power supply enable circuit. Like normally, if the power supplies are disabled, you can push the power button, and current will run through that path to the power enable thing, which will generate a high voltage on the power supply chips, which will engage, and the ESP-ROM32 will start up. As soon as the chip is started up, it can make its own I/O pin high, and then it'll basically keep the power supply alive. And obviously, if I wanted it to turn to power down, I just cut that line, make it 0, and the power supply will turn off. And this is the audio circuit, and I will tell something about that later. Okay, so this is the PCB. Nice thing of living in China is that your Chinese PCBs have a turnaround time of less than a week, so that's good. Obviously hardware by itself isn't enough. You also need software. I mean, if you want to emulate a Game Boy, then yeah, you gotta have at least some software. So first of all, I want to emulate a Game Boy, so I want a Game Boy emulator. So the question obviously is, which one of the thousands that are out there do I pick? And literally, there are a hell of a lot out there. This is like in half of the list, I think. So I settled on GNU Boy, which is a pretty well-known one. The nice thing about this is, basically, first of all, it's GPL licensed. So it's entirely open source, so I can download the source and I can mess with it, import it, etc. The thing actually is pretty portable. It splits out the main emulation layer from the layers that output video and audio and read input pretty well. So I in theory don't need to touch the emulation layer. I can just modify the input and output layers. And it has good game support. I don't think it supports all games. There are emulators that are better at it, but the increasing compatibility also comes at the cost of lower performance. So you need a better CPU to actually run them. And again, this is a keychain Game Boy. I think 99% is good enough. And one of the most important bits, actually, it's a pretty old emulator. Why is that important? Well, old emulators actually tried to make their emulator run on computers that were even old at that time. So GNU Boy, I actually got references in the source code and the documentation that it had some optimizations in order to make it work on a 486 processor, which is pretty nice because, well, my processor also, it's 2 cores of 240 megahertz. It's extremely powerful if you compare it to another embedded chip. If you compare it to a modern desktop PC, it's nothing. So I need something that at least tries to do its best to conserve CPU cycles. So an old Game Boy emulator actually is a pretty good choice. Another thing I had to do, in order to get those optimizations, GNU Boy actually has a few very intelligent tricks, which unfortunately don't directly work for me because they eat up a lot of memory and I don't have a lot of memory. So one of the tricks is the following. The thing you see here is a tile. It's basically an 8 by 8 image. And all the Game Boy games are basically based around these 8 by 8 images. Like in the background is a whole bunch of those tiles. The little Mario sprite you see is a sprite, which is also a tile. Text is tiles, everything is tiles. So the Game Boy itself stores the tiles in a somewhat compressed way. Every tile can have 4 colors. I mean, the entire Game Boy is 4 color. So basically every pixel is a 2-bit value. And the way the Game Boy stores it is it basically tears apart those 2 bits and stores them each in one 8-bit word, like in an entire row of tile data. The hardware can work well. The nice thing is that this is pretty memory optimal, as in you don't have any bits you don't use, and all in all, the entire tile memory for a Game Boy Color, for example, takes up like in 6 kilobytes. That's nothing. Unfortunately, the hardware has to decode these tiles like in every time it rebuilds the video image. That is 60 times a second. And taking this data and turning it into something you can display actually is a pretty expensive procedure, especially if you have to do it 60 times a second. I mean, you have to combine the bits, then you have to, isolate one pixel, look up the color, etc., etc. So what GNU Boy does is actually a pretty nice optimization. Every time a tile is written, and that usually only happens, like in, for example, when a level is loaded or something. It'll detect that, and it'll at that time take the two images and convert them into an easier to parse image. So it converts them into an image where each pixel is only 1 byte with only 2 bits used. So that 1 byte can have the value 0 to 3, which is pretty easy to do, because if you now need to build your image, you just take that pixel and dump it directly to screen, which is, not that expensive. That takes some memory because the tiles are 8 by 8 bytes. GNU Boy does an optimization where officially the Game Boy has 384 tiles. GNU Boy rounds this up to 512. So in total you lose like in 32K of memory, which is acceptable. Unfortunately, the Game Boy Color also has an option to flip the tile, like in both horizontally as well as vertically. So what GNU Boy does is it basically also... it also caches those 4 ways of flipping the image. And then you get a tile cache that is around 128 kilobytes. That's about 1/4 of all the memory I have available. And I also need to store, like in the Game Boy's ROM and RAM and my own programs, RAM, etc. So that is not going to work. So what I did is I modified this algorithm slightly. Instead of calculating a new tile cache image on the fly, what I did is, as soon as, I basically replaced the tile cache with a number of pointers, as well as a separate tile cache. And the trick now is, if the video hardware runs into, for example, I need to display the image of Mario looking left. At that point, the cache can see, I haven't got an image of Mario looking left yet. And it'll, at that point, look at the video RAM, calculate the image of Mario looking left, and then dump it into a free spot in the tile cache. And it'll then use the lookup table to mark down okay, I have calculated the image of Mario looking left, and it's in the first slot in the tile cache. And the nice thing about this is, for example, Super Mario Land will never ever use a picture of Mario flipped upside down. So it's entirely not useful to calculate the picture of Mario flipped upside down. It's entirely not useful to reserve the memory for Mario flipped upside down. With this approach, if I don't see the program using Mario flipped upside down, I don't use the memory for it. So I can now get away with about 700 tile slots for that. And that means a total memory use of about 46K, which is way more acceptable. Okay, so I did that modification. Apart from that, I also needed to, fill in the ports. Okay, display data, display video this way, do audio this way, etc. And that was basically, what's needed to port GNU Boy to a new platform. I also added, like in a little graphical user interface, if you press the power button, like in Shortly, the Game Boy will detect it, and you can set a bunch of options. And I also created a separate bit of firmware, which if you hold down like in one of the keys and then start up the Game Boy, it won't boot your ROM, it will boot up a web server. So you can connect to your little Game Boy, it will act as an access point, go to a web page and upload a new ROM or upload a firmware update. Well, one of the things I've skipped is audio, because that was actually more complicated than I thought. The reason is mostly because of this schematic. And what you see here is two lines which connect directly to the ESP32 and a speaker which connects directly to the chip in the middle. Now you'll probably think, like, in the chip in the middle, that must be some kind of amplifier or, you know, interesting codec or something. It's not. It's actually a motor driver. So why did I use a motor driver? Well, you have chips that are perfectly, okay for this purpose. They have like a nice 24-bit I2S input and can produce really high fidelity outputs on a speaker, like indirectly. The amplifier is integrated. But they all have footprints like this, like in either their BGA or LQFP or something, which is really small. Aside from that, they're also pretty specialty chips, and getting them in China is kind of sort of hairy. These motor drivers, they're used everywhere in like CD-ROM drives, etc. So, yeah, you can get them per thousands, and yeah, you can get them like immediately. So how do I control the speaker? Well, I control the speaker using PWM, and for most people this will ring a bell. For the people who don't, what I basically do is, if I want to send the signal in the top to the speaker, what I actually do is I send the signal in the bottom, and the signal in the bottom is a pretty high frequency square wave. And the nice thing is that in theory, the speaker can't render the high frequency. So instead of going like in up and down very quickly, it will hang somewhere in the middle. And depending on if the high pulses are bigger than the low pulses, it'll either go up or go down a bit. So in theory, with this signal, the speaker should do the exact same as if you put the top signal on it. Well, unfortunately, there's a problem, because, you know, in theory matches practice precisely, but in practice that's not the case. So what I basically got is the problem basically lies in the fact that if you don't output any signal at all, you want the speaker's conus to be exactly in the middle. And in order to do that, you will feed it a square wave that is like in 50% of the time high and 50% of the time low. Now, in theory, if you have a speaker which you can model as a coil, you should get a current that looks slightly like this, and the bigger the inductance of your speaker, the lower the current is. And because the current is so low, in theory, you shouldn't really have any power usage in the speaker. Well, as you may have guessed, the practice is slightly different from theory, and I did have a fair amount of power consumption in the speaker. Those things are not supposed to be 90 degrees. So, yeah. A few broken speakers later, I decided I really had to do something. And I decided to look up, normal Class D amplifiers, like in professional ones, also use this setup. And they don't have a problem with blown up speakers, at least not that I know of. So they must use some sort of filter network or something. So I did some Googling on Class D filter networks. And I ended up in a document like this, and it gave me two filter networks. But the interesting thing is, it gave me one filter network for AD modulation and one for BD modulation. So I'm like, what the hell is AD and what the hell is BD modulation? Well, it turns out that, like in the modulation I had is the standard PWM, which is called AD modulation. BD modulation actually is tri-state modulation. You can either send out like in your power supply or your negative power supply, but you can also send out a signal in the middle. And the way this works is basically this. You have like in a high signal, and if you want your signal to be positive, you will send more larger high signals. If you want your end signal to be negative, then you send more and larger, like in negative signals. And the nice thing is, if you want your speaker to do nothing, to stay in the middle, then you don't send out anything at all. So your voltage over the speaker is zero, your current is zero, and the thing won't heat up. So I basically used this that actually took some effort, because I basically initially abused the I2S peripheral as a PWM generator, and the problem is that thing can only generate one output. So I actually modified this to the RMT peripheral, which is meant to hardware accelerate basically the sending of those infrared remote control signals. It's really widely abusable. If you're into signal generation by using weird hardware, I can highly recommend looking into this. So yeah, I basically could send out like in 2 signals to the motor driver, and the end signal over the speaker would look like this. So you have a neutral, and you can make it go high and you can make it go low, which is exactly what I wanted. And with this, I got a fairly possible sound output without, blowing up any more speakers. Okay, so onto the case, because I have a nice PCB, but I can't have that dangle on my keychain without it, getting broken in seconds. So first of all, what do I need? Well, I do have a Game Boy Color, but unfortunately at the time of designing this, that thing was on the other side of the world, back in the Netherlands. I am in Shanghai, so that's not going to be it. Luckily, you have an overflow of Game Boy Color images on the internet, so I decided to just use that. So yeah, I downloaded 2 of them, 2 semi-random ones, one from Wikipedia, the other one from a website, which name you can't read because that's not English. Dropped them into Inkscape, rescaled them to fit the intentions I want. Then drew a bunch of outlines, and then basically did the same thing for the PCB design I had. And the idea is that if I have the outlines for the PCB design, I can 3D model my PCB, so I can make sure that my PCB doesn't intersect with a bit of case. So I took those polygons, I dropped them all into OpenSCAD, which is a parametric 3D modeler, pretty nice. I use those things to basically build my 3D case. This is the outside of it. And because I have the PCB, I could also inspect like in how the PCB would go into the case pretty nicely. So finally, I could also get the insights like in working perfectly. And well, this is the end result. I then, my work luckily has a 3D printer, which is a Formlabs 1 Plus, I think, which is pretty nice. It's a resin-based 3D printer, which is good because I am not that impressed with the plastic squirty things. And the end result was actually pretty good, especially if you consider this is the first 3D print I did ever. It's as you can see, the resolution is pretty nice. You can actually see the little grip handles in the Game Boy cartridge there. There are also some slight problems. Seemingly, there were a few bubbles in the resin. So yeah, there are a few things that aren't that nice, but still, it's pretty possible. Also, the Game Boy Color has a nice black bezel around the screen. And also the bezel has a transparent part which acts as a screen protector. I also wanted one of those. And my solution was, okay, I basically grab a bunch of transparency sheets. Yes, you can still buy them. Take an image of the original Game Boy Color bezel, shrink that until it was the size that I needed, and then just use a color laser printer to print it out on the transparency sheet. And the transparency sheet actually is thick enough to act as a protection screen, and the bezel looks pretty nice. So I basically cut one out and glued it to my 3D model. Finally, the hardware. I had the ESP-ROM32 module, which is pretty nice, but it only has 4 megabytes of flash. And the nice thing about, like in the ESP32 chips and also the ESP8266 is that the flash is external. You can basically, if you can get to it, you can basically desolder it and replace it by another chip. The ESP32 supports up to 16 megabytes of flash, so I was like, okay, let's dump that in, because 4 megabytes, I know that there are Game Boy Color ROMs that are bigger than 4 megabytes. 16 megabytes, I'm pretty sure I can get most of them in. So how to do that? Well, I have a hot air rework station. I just pointed that on the shield, and then held the shield with a pair of tweezers, and just heat it. And then the PCB dropped out, and I lost a whole bunch of components. Yeah. Okay, so second try. In the end, I got everything working pretty well. I happen to have more ESP room 32s than just one, luckily. So in the end, I used a hot air rework station to get the old flash out and put a nice 16 megabyte new flash in, which is also a bit thinner, which is good because the Game Boy Color is pretty cramped because it's so small. So, onto the PCB. The PCB has a whole lot of SMD components which are pretty close to each other. Normally, I solder SMD components by just using my old iron and just the manual way, but this time I decided to do it using a slightly different route. I don't have a PCB oven yet, but I do have a rework station, so I can go the way of basically applying solder paste, like I did here. Then dropping the components in place, and finally just moving the hot air rework station over it. It's not entirely ideal because as you probably can see, I've singed some of the buttons slightly. On the other hand, the buttons still work perfectly fine, and they're gonna be inside the enclosure anyway, so no one will see them. Well, except for you and the guys watching the video at home. Also a thing, the power button. You may have seen in the PCB that I've left an opening which basically cuts through to vias. And the reason for that is that I can mount an SMD power button inside the PCB. The two little pads for the button basically poke through the via, so I can just fill up the vias with solder, and then the entire thing is pretty solid from an electrical connection standpoint. And also because the button is basically pressed against the PCB, the mechanical connection also is pretty solid. You can press it pretty hard, and you're pretty sure that you don't break any solder bonds. So, finally I put everything together, and obviously the question is, what does it look like? Well, I actually have one here. That's the size. So I would say I succeeded in getting it in keychain sized. Also, the question is, does it work? Well, obviously. So here's a demo. My apologies for the sound. I recorded this in a noisy apartment. So this is Tetris. I have to enter a name because I don't save non-volatile RAM yet, so Tetris forgets my name every time I boot it up. But it does work. Yeah. And actually, you would say that buttons that tiny are pretty non-ergonomical, but they aren't half bad. It's I actually had times that I was beta testing for way longer than I should have. So yeah, that works. But we're not there yet because, this is a tiny Game Boy. So running Game Boy cartridges is one of the things it should do. But we have a 240 megahertz dual-core processor in it. I just knew I had to write some more software to do other cool, interesting things. So I actually did. I wrote some very cool software, and these are the results. For example, this is a Super Nintendo emulator running Super Mario World. I hope you can see it. Yeah, I died pretty quickly. So that worked pretty well. Well, one of the other things people always want to see running on things are... One of the other things is Doom, and the frame rate is atrocious, and the controls don't really work because it lags, etc. But still, it is 3D. It works perfectly fine. So I was like, I have one 3D game patched down. What game do I have installed which is a step up from Doom? I know, The Witcher 3. That's probably a good one. To quote someone, focus you. So yeah, again it lags, but it works perfectly fine. This is a pretty powerful Game Boy, and I have to say that it runs my VNC forwarder software pretty nicely. So yeah, if you didn't know, this is the trick. I have a gaming rig which runs a VNC server. Then I've written a tiny little program which takes that image, rescales it until like in the size of the OLED, and then uses Wi-Fi to forward it to the Game Boy. The Game Boy catches the key presses, forwards that back to the server, which sends it to the VNC server, which simulates the key presses on the PC. And that's the way I can play The Witcher 3 on a screen this size. Okay, so that is pretty nice. Unfortunately, I couldn't finish the entire Game Boy thing in the way I wanted before the presentation was here. So I have a few things I still need to do. And well, first of all, the web server is a hack. Like if you go to the web server, then this is the initial screen. You get a bunch of broken pictures and an intro screen that isn't even valid anymore. So I still need to do something about that. The second bit is charging. At the moment, I have a nice black and red wire sticking out of the Game Boy, and you need to apply 5 volt there in order to charge the thing. That's not what I originally intended. My original intention was to basically do wireless charging. So basically, you have a coil that gets an AC voltage, and then inside the Game Boy, you have another coil that uses the magnetic field to generate another AC voltage. And with a bit of luck, you can get like 5 volt, 100 milliamps. That's the goal over. I don't have the 5 volt part down entirely. I'm slightly lower. So yeah, that is still a to-do. Finally, there are still a few bugs in it. Because of the architecture, 4 megabyte ROMs don't work yet. In theory, they can, but I still need to write the code for that. Also, sound, as you may have heard, is slightly off. There is something weird going on with buffers there, so I need to fix that. And finally, you saw me enter my name there in Tetris. As I stated before, I have to do that every time because Tetris has RAM in the cartridge, which is non-volatile. And it usually stores the name there, so the next time you boot up the game, you can just, it'll remember that you entered your name. The emulator doesn't do that yet, so that's also something I need to fix. I also have a bunch of nice to haves. Like in this chip can also do Bluetooth. I think it would be nice to, for example, you could have an Android application that emulates some of the more advanced stuff and then use Bluetooth or something to send it to the little Game Boy. That's probably also fun to do. The battery life at the moment is like in an hour. I can probably push that up by optimizing my program a bit because at the moment both cores are running on 240 megahertz like in all the time, which is kind of, not that good. And I probably can think up a few other optimizations as well. Finally, this thing is going to be open source. As soon as I've cleaned up the code, I'm going to release it under the GPL. I'm also going to release the 3D printer models under the GPL. So if you have a 3D printer, you can just print your own tiny little Game Boy if you want to. And as soon as it's done. And finally, thank you very much for listening. And I hope you enjoyed the talk.
Jeroen Domburg, everyone. Let's give him one more round of applause.